All right. Hello, my name is Zach Hofstad. Today I am presenting On Thin Ice, Oceanic Heat Impact on the Arctic Tundra. This is an analysis that deep dives into oceanic heat levels within the Pan-Arctic ocean environment. The analysis stems from data from a NASA study spanning 33 years that collected heat level and heat absorption data within 3 oceans in the Pan-Arctic environment. The objective of this analysis is to not only further understand the oceanic heat trends within the Pan-Arctic, but to also potentially attach those trends to the current state and climate conditions of the Arctic tundra within the Pan-Arctic area. So within the analysis, we first want to specify the summary of the importance of the Arctic, its climate, and oceanic heat as a climate driver. The second component of the analysis is the data and insights derived from the analysis. And the final component is recommendations and next steps stemming from those insights and of the data. So setting the stage first, what is the importance of the Arctic, its Pan-Arctic region, and the oceanic heat as a climate driver, specifically in this case to the Pan-Arctic region. The Arctic and the Pan-Arctic landscape plays a very large role in our planet's climate balance. The Arctic is a very large icy and white geography, and naturally it serves as a reflector of the sun's inbound heat from space. So as the sun sends heat to planet Earth, the Arctic actually plays a role in reflecting that heat back into space, in turn cooling the Earth's atmosphere and supplying some equilibrium to the planet's climate. Over time, the Arctic has seen trends that is indicating it is rapidly warming, and in turn, its largest biome, its tundra permafrost, which is underneath the ice and snow of the Arctic, the tundra is also rapidly warming. Due to this, more of the tundra is being exposed. So increased exposure increases the levels of greenhouse gases and carbon dioxide entering the atmosphere, thus leading to increases in climate warming in the area. And as it pertains to oceanic heat specifically as a climate driver, we need to know the oceanic heat content to not only know how the oceans are, what patterns the oceans are exhibiting and showing over time, but how that content is potentially affecting its neighboring regions, and in this case, how it's affecting the Pan-Arctic environment and how it could be potentially leading to climate warming and how it's potentially influencing the tundra biome within the Arctic. Okay. Entering the data now, we wanted to understand further the trends, the heat absorption and heat level trends within the oceans of the Pan-Arctic. So how are these oceanic heat levels shifting or not shifting over time? And how are these heat levels potentially affecting the tundra landscape within the Pan-Arctic region? So the data indicates that in all 3 oceans measured in the study, so the North American, the Arctic, and the Eurasia oceans of the Pan-Arctic region, all 3 of these oceans have shown rising heat levels within the 33-year time frame of the study. Heat content averages rose between 9.5% and 17% from 1982, the earliest point of the study, to 2013, the latest point of the study. And that is for all 3 oceans measured in the Pan-Arctic region. So now that we know that all 3 oceans showed rising heat temperatures or heat levels, we wanted to also quantify what those levels were over time. Illuminating the data via visualizations showed that the Arctic Ocean showed a 17% increase in heat levels from the first time period interval of 1982 to 1990 to the latest, which is 2001 to 2013, the North American Ocean showed nearly 14% increase in heat levels, and the Eurasia Ocean showed nearly 10% increase in heat levels. And in this study, heat levels were measured in MJM2 units, which stands for megajoules per square meter, which is a common instrument of measuring heat in ocean capacities. We also wanted to understand how and when heat is at its highest and how the year behaves with the different and how the heat changes over time or doesn't change over time within the course of the year for these three oceans. The data shows that the heat levels in all three oceans tend to increase starting in May and April months, peaking in September at its highest and most warmest, and start to fall in the October months. So that pattern is consistent with all three oceans and all three time intervals of the analysis. So 1982 through 1990, 91 through 2000, and 2001 to 2013. So the key takeaway is that after understanding the data and visualizing the data, we now know that heat levels are increasing over time for all three oceans of the Pan-Arctic area. And the next step is to accompany this data with additional data that could provide some light on how the oceanic heat is impacting the tundra landscape within the Pan-Arctic specifically. Visualizations were a critical component in understanding this data. These visualizations show a time series approach by year. And as you can see, the 2001 to 2013 time interval was the highest and most warmest month or most warmest time period for all three oceans. Bar graphs were used to indicate heat averages within each interval of measurement, showing the increases of heat over time for all three oceans. And heat maps are also utilized to understand which months of the year were the warmest and which months of the year were the coolest for all three oceans, and the exact heat levels in megajoules per square meter as well. So now that we understand that the heat levels are rising over time for the three oceans, the next step is to attach that quantifiable data with additional data that could correlate rising heat levels of the oceans with the deteriorating characteristic of the ocean, of the Pan-Arctic tundra. So next steps we would love to do is to not only continue the scope of this analysis for another 10 years, adding a 2014 to 2023 interval to continue to see if the heat levels continue to rise for all three oceans, but to conduct supplemental analysis by appending these insights of rising ocean heat with additional data such as ocean depth and spatial data, so merging longitudinal, latitudinal, and depth data with the oceanic heat data. We also want to append and gather more data around other climate drivers, such as sea level rising and melting ice levels, to append to the existing data as well. And we also want to attach activity-based data. We want to see if the rising heat levels of each ocean in the Pan-Arctic region was potentially caused by natural and human-caused events that could potentially influence those climate patterns. So that concludes this analysis. Thank you so much for the opportunity, and let me know if you have any questions. Thank you.